The broadcast is now starting. All attendees are in listen-only mode.
On behalf of RBCS, RBCS New Zealand, RBCS Australia, and Software Test Works and Software Test Professionals, we welcome everyone today to this webinar on advanced software testing, static code analysis. I am Rex Black, president of RBCS, a worldwide testing and quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. Since 1994, RBCS has been both a pioneer and leader in quality hardware and software testing. RBCS has offices in the United States, New Zealand, Australia, and Sri Lanka with partners around the world. RBCS delivers insight and confidence to our clients, helping them get quality software and hardware products to market on time and with measurable return on investment. RBCS has a team of international consultants that deliver customized training, consulting, and outsourcing services for companies that are looking to improve their test and quality assurance practices. RBCS has helped hundreds of companies reduce development and support costs while assuring the best quality products are delivered to customers. I'm the author of Pragmatic Software Testing, Advanced Software Testing Volumes 1, 2, and coming very soon, Volume 3, Foundations of Software Testing, Critical Testing Processes, and Managing the Testing Process. I hold a degree in Computer Science and Engineering from UCLA. And I'm also past president of the International Software Testing Qualifications Board and the American Software Testing Qualifications Board. RBCS is presenting this webinar in partnership with Software Test Professionals. If you haven't visited their association website, make sure you check it out as well. www.softwaretestpro.com. That's softwaretestpro, all one word, .com. Before we start the presentation, a couple housekeeping notes. If you have any questions during the course of the webinar at any point, go ahead and submit them via your webinar interface. You should have a little questions box that you can submit questions to. There is no need to ask for copies of the presentation. The presentation will be on the web at our website, www.rbcs-us.com. It's on the basic library page, which you can find in the resources tab on our home page. There is also no need to ask about how to register for the free e-learning. Just by attending this webinar, you are automatically registered. So check your email over the next couple days. Watch the spam filter to make sure that the notification doesn't get lost. You will have a limited amount of time to respond if you are the winner, so make sure you check that. If you're having any problems with either the audio or visual components of this webinar, please contact GoToWebinar support. If, for whatever reason, you cannot get to the webinar online, or if you're dealing with an unreliable connection, please download the slides from the basic library. Again, that's at www.rbcs-us.com. Basic library is found on the resources tab. And be sure to use the telephone to connect rather than voice over IP, though we don't seem to have a whole lot of problems and very few reports of technical difficulties, and most of the time it's due to firewalls blocking people's ability to access the webinars to begin with. I hope you enjoy this free webinar from RBCS. We do these free webinars as a service to the software testing community because at RBCS we're a not just for profit company. Okay, today's presentation is on static code analysis. So what is that, you say? Static testing is any form of testing where the item under test, which in this case is a code module, is not actually executing. Static analysis is distinct from reviews, which are another form of static testing. A review involves the finding of defects using teams of people who are scrutinizing the item under review, while in static analysis, the scrutinizing is done by a tool. And these tools can look for various kinds of problems, and in this webinar, we'll examine how to use static analysis to find defects and improve the quality of the code. I'm not going to get into specific tools. This is something that often comes up of, which tool would you recommend? We're happy to work with clients to help them determine which tool is the best fit for them, but there is no one best tool typically. There are too many variables that go into making a proper tool choice, and in some cases using a tool is not even the right place to start. But this webinar should make you better able to judge the capabilities of the tools and decide if you do want to use one. Okay. So this is, for those of you who have just joined us, as it were, in this series. It's been a series of webinars going back until, I think, like the middle of last year, summer of last year. Started to do a advanced software testing series, and that was excerpted. Originally, it was excerpted from the book Advanced Software Testing Volume 1, which was the business-oriented test analyst perspective on testing, and then we switched over at the beginning of this year, late last year, I forget which, to looking at these things from a technical perspective. So this is coming from a technical perspective, which is the topic of Advanced Software Testing Volume 3. So, as I said, the initial ones, the initial webinars in this series were very much black box focused. On black box, we're talking about behaviors of the system, how the system affects users and customers and so forth, and outputs it produces and those sort of things. Things they're externally visible. Now, we also had looked at in a previous one of these webinars some white box techniques and looking at things like code coverage, which is a good way to make sure that certain parts of the logic of the application have been properly tested out. Now, in static analysis, what we're doing is we're looking at the code directly, trying to find defects in it, but we're not doing it, that's the right word here, as people. It's not a human activity per se, and the defect detection is not, other than that we start off executing a tool. Now, you might be saying, well, if we're going to do this with a tool, what do I need to listen to this webinar for? Isn't the tool going to tell me what I need to know? Well, as was the case with code coverage, for those of you who were there for that webinar, while the code coverage tools can tell you something, they can give you a metric, most people have some difficulty understanding what that metric is. And the same is true with static analysis. Then unless you understand how to use the tool properly and how to interpret its results from a I want to say theoretical basis, but it's not theoretical, but in terms of grasping what it actually does, it's very difficult to use it properly, and you get a lot of misapplication of this. And this is not just true of static analysis tools. It's true of many different kinds of tools, test automation tools, and even tools that are used by people other than testers. If you do not have a grasp on what it is that the tool is doing, it's difficult to use the tool properly. Now, static analysis, it certainly can be thought of as a form of testing, and sometimes people say, well, okay, it's testing, but it's being done by a developer, so it's not tester testing. And well, that's true. It can be done by a developer. It can also be done by a tester. Not really too interested in this webinar about the question of which group or which person in the team should own this task. It's more focused on what are the things that this can do for us. Now, like dynamic testing, static analysis, as again, is a form of testing, a form of static testing. It is looking for defects, but as I said, you're not actually executing the system. Now, the thing that's nice about this, I guess you could say, is that when you're doing dynamic testing, and dynamic testing is testing where the system is actually executing. When you're doing dynamic testing, what you see are usually not defects, but rather the symptoms of defects, the failures that the defects cause. And this means that in order to repair the defect, there is a fairly lengthy process of debugging that has to happen in order to locate the underlying defect that caused the failure. And that can be a rather expensive process. It can be very time-consuming. Certainly not at all unusual to find that, it's the amount of time required from developer side and tester side and so forth to deal with a defect found in formal testing, like a system test or something like that, after it's been handed off, can easily get to the 10, 20, 30, 40 person hours range on average of effort, depending on complexity of the system and so forth. Now, in static analysis, like as in reviews, you're actually going to be looking directly at the defect. The tool is going to come back and say, this is wrong. Now, there is the issue of what are called false positives, which I'll address a little later. But a false positive in general is a case where the tool flags something as a problem, and it's actually not a problem. It's something that is the way it should be, or is the best possible solution. Now, yes, there's going to be some amount of those, but excluding those, then what you're looking at, the remainder are actual defects. There is no debugging process that has to occur. It's just a matter of going directly into the defect and resolving it. So that means that they tend to be a very cheap way of fixing defects. And of course, it's even cheaper than a review, because in a review, typically there are multiple people involved, whereas a static analysis is being done often by a single individual, say a developer running static analysis on their code after they've written it. And that is a very, very quick and very cheap way of removing defects. Now, static analysis also has the advantage of being able to find defects that don't tend to show up in dynamic testing, or that they might show up, but they show up as failures that are really difficult to isolate back to the underlying defect. You know, like maintainability issues. If the code is not being properly written, I mean properly from a maintainability point of view, it's difficult to change, it's difficult to analyze the code to understand what it does. What you will tend to see is that over time you're going to have an unusually high rate of regression failures occurring. Excuse me. Now, you can see that pattern over time if you've got your defect tracking tool set up properly. As you see, wow, you know, we have a lot of regression failures. But as far as like helping you understand where exactly that failure is in the code, where the problem is in the code, excuse me, the maintainability defects, won't really tell you that. It'll just tell you, yeah, the code's brittle and it breaks really easily. Static analysis tool can actually pinpoint for you, look, here's the code that is difficult to maintain, and here's why. Also things like pointer problems, or you know, other kinds of questionable constructs, certain kinds of data flow issues could result in really weird intermittent failures, but serious failures, reliability issues. Those will be can be caught by the static analysis tools. And as I said, when they're caught directly. They're not caught in the form of a failure that has to be painstakingly tracked down to the underlying defect. Rather, they're caught in the form of pointing at the defect itself and saying, here's what's wrong. Now, what can be subjected to static analysis? Well, certainly the thing that we think of most often is program code. You look at taking some C++ or some Java, something like that, handing it to a tool, saying, here, you know, check for cyclomatic complexity, check for coding standards violations, those kind of things, which we'll talk about in a minute. So I venture a guess that most times when people say the phrase static analysis, or when they hear the phrase static analysis, what's in their head is exactly that. But we should not assume that that's the only form of static analysis that is interesting and useful. For example, here's another form of analysis that I've seen done. This is performance simulation. So you build a model of the program, or perhaps the system of systems in the data center. There's a tool, for example, called Hyperformix that I'll just mention. Not that I'm endorsing it, but just that I've seen it used before to do this. You build a model, and then you can run a simulation of how the system will respond under certain kinds of load, and it generates these hypothetical loads and runs them through. And a hypothetical based on some model that you have of a number of simultaneous users and the amount of load associated and so forth. And it can generate estimated performance results. So that's a form of static analysis, because, again, you know, notice the tool's doing the work, and the item under test, in this case the code or an entire system of systems in a data center, is not actually being executed. There are also various forms of HTML and XML parsers that can read HTML, XML format inputs and let us know various things like, are they grammatically correct, are they conforming to the standards. For example, the w3c.org website has some tools, automated and free tools, that allow you to check for HTML compliance and broken links and those sort of things. Now, you might say, well, you know, if it's actually traversing a website, isn't the website in effect executing? Well, I don't know. I mean, if you're going to call it executing, I guess you could, but it's certainly it's not executing in the sense of evaluating the performance or evaluating the behavior of the system, other than just the validity of the links and so forth. So usually that's classified as static analysis, and it is another form of it. And requirements and design documents can and should be subjected to static analysis. For example, if you use Microsoft Word to edit a document, one very good practice before declaring that document done and ready for a review is to run the spell and grammar checker on it, and make sure you got the readability analysis metrics turned on. And so, of course, resolve any spelling and grammar problems that you find, because those can be distracting to readers. And also make sure that you take a look at the readability metrics and see, hey, if this document written in a way where we've got a lot of long sentences and a lot of complicated sentences, it's going to be beyond the ability of the audience to read. You know, I mean, if you're working in a multinational type of workplace, and of course a lot of us are these days, it's quite possible that these documents will be passed around to people who might not be as, I don't know what the right word here is, facile, I guess, at reading complicated documents in English. And so you might want to have a standard about keeping the reading difficulty below a certain number for documents that are going to be shared internationally. So that would be another form of static analysis. So I'm going to talk about things that are more along the lines of what we typically think about when we think about static analysis of code. But keep in mind that static analysis can go well beyond just analysis of code. Okay, what are some of the benefits that we can hope to enjoy from static analysis? Well, as I said, earlier and cheaper detection of bugs before we're actually executing tests. And the bugs are detected directly rather than being detected from their symptoms. The whole isolation and debugging process is short-circuited, which ends up saving us a lot of time and money. Now, there is this principle in testing, which long-time listeners will have heard me refer to one time or another in the past, which is called bug clustering. And this is a very long-standing observation that defects are not randomly and evenly distributed throughout the code, but they exist in clusters. And what I mean by a cluster is that the defect density, the number of defects per 1,000 lines of code, say, if you want to measure it that way, or defects per function point if you prefer to measure it that way, is variable from one module to the next, and exhibits actually very significant variation, where a very small number, typically less than 20% oftentimes, of the modules will account for more than 80% of the bugs. And this can be because we've got a dangerous programming techniques being used, very long modules, lots of go-tos perhaps if you're dealing with very inexperienced programmers who might do such things. The overall high level of complexity, which we'll talk about in a little bit. This can really help pinpoint the location of potential or actual bug clusters and set in motion in an effort to eliminate those. As I said, we can locate bugs that dynamic testing might miss, or we might find them in the form of intermittent failures or other kinds of shadowy sort of symptoms of what's going on, like high rates of regression and so forth, but it can be very difficult to track down. When in a static analysis, as I said, will point directly at them. I've mentioned the issue of dependencies and inconsistencies, like link problems and so forth, so that's another thing that we can find very easily. Using a link checker on a website is obviously a lot cheaper than paying someone to manually traverse the entire site. In the long run, the use of static analysis will lead to improved maintainability of the code as we clean it up and bring it more into compliance with industry best practices in terms of complexity and coding standards and so forth. And not only that, but actually we can, if we gather metrics on the kinds of problems that we're having and look at, okay, well, what does this tell us about the type of problems we're introducing, then you can introduce preventative measures in an organization, such as training for the programmers or designers on how not to create certain types of defects. And certainly that's true of any sort of testing, but we can always look for patterns in what kind of problems we're finding and say, oh, okay, well, let's try to eliminate these patterns. The nice thing about static analysis is it's talking about static analysis of code. We're going to be looking directly at the problem, as it were. So if we're doing static analysis of code, what are the kinds of problems that we would expect to find? Certainly one of the things that can be caught is the possibility that a variable could be referenced before a value is set. Now, in some cases, a compiler will take care of this for you. In other cases, it won't. So, if you're using a relatively weak compiler that will allow a lot of things to slip past you, for example, C is notorious for this, static analysis tools can strengthen the checking that you do on it, make sure that some of these things will not get past you. Now, of course, in a more rigorous language like C++ or especially Java, there's a lot of static analysis that's done by default by the compiler. And that would include this issue of interfacing between the modules and components. In some situations, it's possible to attach just about anything to anything and try to get data to flow through it. Fairly structured languages like C++, Java, they're going to try to enforce consistency. But of course, if you're connecting to a component that's external to the code itself, then the compiler and linker have no way of knowing what exactly you're interacting with, and there's no way of checking this, and the static analysis tool might be able to check it. Dead code and dead variables are other things that can be located and potentially then removed if appropriate. Situations where logic is missing or wrong. For example, if you've got a possibility that a loop might iterate more times than it should, or not terminate, that's something that could be caught. As I said, complexity analysis is something else that we can look at, and I'll show you an example of this in a bit. Programming standards violations. This is probably the most visible, if not most used, application to static analysis now, where you have static analysis tools that have certain rules about good programming standards, for everything from variable naming conventions to indentation to you name it. They can enforce it, and that certainly is very useful, because it will help greatly improve the maintainability of the code if you get them all to comply with industry best practices in terms of programming standards and so forth. There are some issues associated with doing that, which I'll discuss a little bit later, but definitely it's an excellent benefit of static analysis is getting the code all in a more consistent best practices kind of form. We can find security vulnerabilities in static analysis. For example, if the code is vulnerable to what's called a SQL or SQL injection or buffer overflow, then the tools can find that. And again, when you're dealing with situations with a weak compiler, various kinds of syntax violations that might slip past the compiler can be caught. The typical example here being C and the old tool that was used way back when in the Unix days with that, which was called lint, was basically a way of making up for the I don't want to say sloppiness, because this wasn't a mistake on the part of the designers of C. It was deliberately designed to be a very permissive and relatively low-level language, and thus you were allowed to do all sorts of things which weren't necessarily a good idea, but which might, under certain circumstances, such as creating an operating system, actually be necessary. So you could use a tool to catch problems. So if you are using a programming language that is not very good about type checking and interfaces, checking of interfaces and so forth, when between caller and calling functions and caller and callee functions, excuse me, make sure that you backstop that with some static analysis. Okay, so as I said, typical users of static analysis tools would be programmers, and this would often happen during unit or integration testing, though certainly there are design tools and architectural tools, like I talked about, the performance modeling tool that can be very helpful and is something that can be used. But because these are the typical uses, again, don't forget that there are many other uses that are out there, and don't think, oh, static analysis, well, that's just for programmers and designers. Now, this issue of false positives, if you've got a static analysis tool and you roll it out against an existing code base, one thing that you will tend to find is a high rate of false positive. Now just be specific. I've mentioned this before. Get a little more specific here. This false positive, what I mean is the tool comes back and it says, here's a problem, and violation of coding standard or something like that, and it can't really tell you in all cases whether the problem is actually something that absolutely must be dealt with. In many cases, it's not necessarily, if you're talking about existing code. I mean, if it's existing code and the system tends to work pretty well, then apparently the static analysis violations are perhaps not causing a problem, and even though there might be a very large number of them. So you have to be really selective about which ones you're going to tackle, because you wouldn't want to necessarily create behavioral problems in the system in the name of quote-unquote cleaning up the code. And so this is a risk of static analysis tools, and something that when you initially roll them out, you want to be very very careful about. Okay. Now, static analysis and dynamic analysis. Sometimes there's some confusion about this. People go, well, I've heard of static analysis, and I've also heard of this thing called dynamic analysis. So what are we doing? What is different there? Well, dynamic analysis would be the code that you're testing is actually executing, and you're trying to watch for certain kinds of failures that might occur. So dynamic analysis can include things like looking at the percentage CPU utilization while a program is being tested, or looking at looking for memory leaks while a program is being tested, looking for pointer problems while a program is being tested. So they are actually quite different things, because the static analysis is actually looking at the code. The tool is looking at the code and looking for specific problems in the code. Dynamic analysis might involve instrumenting the code in order to enable capture of certain types of things, but it's actually looking at how the code is affecting the environment in which it operates, I guess is the right way to put it. The other cohabitating systems and the hardware and operating system resources and so forth. So they are very different things. Well, let's look at an example of a kind of analysis that you could do, cyclomatic complexity, this is sometimes called. Now, this is becoming more popular. We've had some of our clients, particularly clients that are doing agile programming, mentioned to us, hey, you know, we've decided to start using cyclomatic complexity metrics, and we're setting a target. The cyclomatic complexity should be no higher than 10 on any of our new code that we write. And so you might be hearing about this, or at least reading about it, and thinking, okay, well, what is this? What is this telling us? What is cyclomatic complexity? Well, cyclomatic complexity is it dates back quite some ways to the mid-'70s, when a guy named Tom McCabe was trying to figure out why programs were so hard to write, at least hard to write in the way that they would work. And he came up with this theory that a pretty good metric for the difficulty of understanding and therefore creating a program could be modeled, if you will, measured, based on the amount of branching that happens in the program, basically the decision points. He said every time you get to a decision point, you know, the program has to do one thing or another. And the human brain tends to be limited to about 7 to 10 pieces of information that it can keep in its active memory at any given time. It's the frontal cortex that does all of the analytical thought for the brain. It's limited to about 7 to 10 pieces of information. So he said that once you get to the point where you've got more than 7 to 10 decision points in a module, that's going to start to overwhelm the programmer's ability to keep straight what has and hasn't happened, or what will or won't happen, and the programmer will start to make mistakes. So that's a good general approximation. Now, of course, you know, I mean, we could always argue that there are other things that make programs complicated, and in some cases, it's the obvious thing to do is to have more than 10 decision points, because the decision points are kind of related to each other, and it's just that the code makes them look different and so forth, which I'll mention an example of that in a minute. But, you know, it's a reasonably good surrogate metric, if you will, for getting a sense of which modules are more complex than others. Now, what does this tell us? Well, certainly if the complexity as the complexity goes up, the likelihood of regression in the module probably goes up. It's harder to understand. It's harder to maintain. There's some controversy about that statement. There's a contradictory study from IBM that came out in, I don't know, like the mid-2000s. But other than that, all the evidence seems to suggest that as cyclomatic complexity goes up, the regression rate for a module also goes up. Also, the complexity, because it's related to decision points, is very closely related to decision coverage. So those of you who tuned in for my white box testing / code coverage webinar will have heard this term before, of decision coverage, or branch coverage, it's also called. Basically, once you've calculated the complexity of a module, that is typically equal to the number of tests that are going to be needed to get statement coverage and decision coverage. And so it's a good rule of thumb, I guess you could say, for determining whether a set of unit tests is reasonably complete. You know, obviously, I don't want to say complete, because anytime we talk about testing being complete, we're often a phantom chase there. But certainly I think a good standard for completeness of unit testing, acceptable completeness of unit testing, would be that 100% statement coverage and 100% decision coverage was achieved. And if somebody's saying that they've done that, but yet their number of tests is less than the cyclomatic complexity of the module, then they probably have not. So let's take a look at how this works. I think this is going to require a little highlighting going on here. Sorry, something very strange just happened on my screen. Just a moment here. Okay, yeah, hopefully you're all seeing this properly. Huh, that's something very unusual. Okay. Having some technical difficulties here with the presentation. Hopefully you're seeing this code. Excuse me for just a second. I want to make sure that you're actually getting this. Yes, you are. Okay, good. There are 4 ways to measure the cyclomatic complexity of a piece of code, and I'm going to give you the first 2, which are the formal ways of doing it, and then I'll give you a good rule of thumb, and then I'll tell you what the easy way is to do it. So the formal way to do it is to take the code, which you see an example of some open source code here, Euclidean greatest common denominator calculator. Takes 2 integers and an argument, and it's going to return back the lowest common denominator, or the greatest common denominator, excuse me, of the 2. So we take the code, and basically for every 0 or more non-branching statements, we're going to draw an arrow, which is called an edge. And anytime we get to a decision point, a branching point, we're going to draw a bubble, a circle, which is called a node. And you start with a enter, because you enter the module, and then you have an exit. We exit from the module down here. You're always going to have the enter and the exit, so you draw those first. If there are no branch points, then you have a straight line going directly from enter to exit, and that's that. But if you have a branch point, as we do here, you'll see that we have that arrow indicating, okay, here's this branch point, and then here's another branch point, and then here's another branch point, and then here's a loop point, which is a form of a branch where we either branch back around to do, or branch around to do the body of the loop, or we do not. Okay, so as I said, 0 or more non-branching statements, so that's, this, nothing here, so we get that. And then if A is less than or equal to 0, we are going to do this path to the exit. We're going to return, if essentially every return is represented by a single exit. If that's false, then we were going to continue on. Notice we don't have an else here, but because we returned, that was essentially this. It kind of creates a virtual else. If B is less than or equal to 0, then again we're going to return. That's another branching off point. Okay, now we know that both A and B are greater than 0. So we go to this chunk of code here, this T, int T. And then we have another branching point, this guy here, B greater than A. And then we have, if that's true, we've got this chunk of code here. Right, if it's false, we go and bypass that. There's no else, but there is a false branch. So we get to the while. And for the while, while something is true, we can do the body of the loop, and if something is false, we'll go on to do a return again. Excuse me. So if we draw this graph, we can then calculate the cyclomatic complexity as shown on the graph there. We can count up the number of enclosed regions. Let's see. trying to graphically illustrate this for you in a way that's going to be, yeah, here we go. I'm shading in these regions. See, this is an enclosed region here. What I mean by enclosed is it's ringed off by edges and nodes, right? Here's another one here. See that? That's ringed off by edges and nodes. There's another one here. And then we got another one in here. Okay, so we've got 4 enclosed regions, and then you add 1. Now, sometimes people get a little perplexed about that. They go, what do you mean add 1? Why are you adding 1? Well, notice that if we had a module that had a single, it had an entry point and an exit point, and there was no branching. So that would just be a single arrow going straight from enter to exit, right? In order to get decision and statement coverage for that module, you'd still need 1 test to cause it to fire at least once. So that's why you're adding 1 here, that even if there's no branching and no looping, you're still going to need at least 1 test. Okay? So in this case, cyclomatic complexity is 5. It can also be calculated, cyclomatic complexity can, via this really ugly expression here, edges minus nodes plus 2. So why is it that way? I do not know. That's some sort of graph theory thing, and it's not something that I particularly remember. But anyway, those are the 2 formal ways of calculating the cyclomatic complexity. And as you can see, for even a relatively simple piece of code like this, it's not necessarily a whole lot of fun. So here's a simpler way, simpler rule of thumb. Can be done by anybody, and many times, even if you have to count on your hands, you've got enough fingers to do it. Basically, go through and count up every branching and looping construct and add 1. So see, we had if, while. So that's 4 plus 1 is 5. Now, to clarify that a little, you count the if, but you don't count the else. Ifs count, but else's don't. Any kind of looping construct counts. A for loop, a while loop, a do while loop, any sort of looping construct, you're going to count for 1. A switch case construct, basically what you're going to do is you're going to count the case blocks, but you're not going to count the default. And that's basically analogous to not counting the else on the if. So usually you can go through and do a very quick scan of a program in 30 seconds or so and count those up and have a reasonably good estimate of the cyclomatic complexity. I've never seen a case where the actual calculated cyclomatic complexity was different than what the rule of thumb gives you. Now, I mentioned 4 ways. You might be thinking, well, what's the 4th, Rex? Well, the 4th is to go out and get a tool and do it. So, for example, on SourceForge.net, you can go and find a open source cyclomatic complexity calculation tool for Java, and that will do the calculations for you for free, which is, of course, very nice. So, this is what cyclomatic complexity is doing for us here. Let me get this back to normal mode here. Yeah. Now, for the same example, I mentioned this. The decision coverage is equivalent to the cyclomatic complexity. Actually, this is what's called the basis tests. Now, to create a set of basis tests for a piece of code, you first define the basis paths. Now, the first basis path will be as shown here on the slide. It's the shortest route through the code. Let me highlight that. So we go A. See, notice that I've got A is the label here, this node, to B. Okay, now I'm here, and then to F. And then for each of the subsequent basis paths, what I'm going to do is I'm going to add, I'm going to take a basis path not previously traveled, but I'm going to try to make the number of nodes and edges, so the bubbles and the arrows, that are covered for the first time in this basis path minimum. I'm going to minimize the number of previously uncovered basis paths, or excuse me, nodes and edges in each basis path. Okay, so I get A, B, C, F, and then I go A, B, C, D, D. Yeah, this is this test number 3. So I go the false way, and then E, and then F, and then add this to the next one, and then in the last one I'm going to add this guy here. And those, I can define the tests to make those happen, which you see right over there. And you can check this out yourself, and you'll see that this also gives you decision coverage. It does not do a very good job of covering that loop, of course, because it only iterates the loop body either 0 times, 1 time, or 2 times, which is certainly not rigorous coverage of the loop body by any means. So, it's usually a good idea to add some more coverage there. That's why I said the statement and decision coverage really ought to be considered a minimal amount of coverage for a unit when you're unit testing it. Okay, so here is a quick exercise for you. We'll check and see how many of you can get this one right, and go to the Q&A session. Maybe you were following along. Take a look at this code. I'll leave it up for just a second and see if you can calculate the cyclomatic complexity of the code. Okay. As I said, we'll come back to this during the Q&A. For those of you who want to revisit this, you should have been able to use the rule of thumb I gave you very quickly to count the cyclomatic complexity for this. Now, there are various tools that can show cyclomatic complexity graphically. You see an example of a simple piece of code versus a complex piece of code in terms of its interconnections. These are modules and their flows, if you will. And this there's a tool from McCabe. After McCabe got done doing his theoretical work, which he did for the CIA, he went off and founded a company which created a tool called BattleMap, which can have call complexity as well as the cyclomatic complexity of the individual modules. And this is when you're talking about designing a system that is good architecturally. You want to look at this issue of call complexity as well. There's an interesting paper on this. If you go out on the internet, I think it's on nist.gov, not gov. If you go out to that site, nist.gov, and do a search there for something called structured testing, or maybe add McCabe structured testing to it, you can download a big long 120-page discussion by McCabe and somebody else, a fellow named Watson, I think, who describe cyclomatic complexity and integration complexity in the paper, and then talk about how to use those for testing. So possibly of interest to you. Okay, so we mentioned using a tool to calculate cyclomatic complexity, which I can think of as its a code's predisposition to be a location of bug clusters, as well as being negatively correlated to testability. Now, what I mean by negatively correlated to testability is that the higher the cyclomatic complexity, the higher the number of test cases required to completely test, but to achieve statement and decision coverage of that piece of code. Pardon me. So that's one aspect of using the tools to improve the quality of the code from a, you could say, low-level design point of view. But it would still be possible to write code that had a relatively low cyclomatic complexity, but was absolutely abysmal stuff, using variable names that just made no sense, like word 1, word 2, double word 1, double word 2. Because all it's doing is looking at the branching and looping constructs and saying, okay, how many of them are there? So it's fairly simplistic from that point. Well, not simplistic. Simplistic's the wrong word. Unidimensional, let's put it that way. It's looking at one single aspect of the program that makes it difficult to write and maintain. But, of course, there are many things that could happen from a textual analysis point of view in the code. And so what we might want to do is parse the code and actually, based on a parsing of the code, see what kind of problems we could find. So here is a tool called Splint, and we have a sample piece of code here. Let me get the highlighter up and we can do a little more illustration of what's going. So Splint's an open source static analysis tool. There are a number of these out there. So let's take a look. This is a simple piece of code that is going to loop around and apparently process a stream of input and look for an X for some reason or another. I'm not sure why it's looking for a lowercase x, but it is. It could be looking for anything in an input string. So what does Splint tell us about this code? Well, it says something very interesting. It says, first one here, variable C used before definition. And as you see, we have this char variable C. And sure enough, we do a comparison check of C against the character value of X, lowercase x, before actually defining it. Okay. So that's not good. Now, presumably, nothing untoward will happen here if you're working in an environment where C, or any variable that's allocated on a stack, which this one would be, gets initialized to 0. But that's not necessarily a good assumption to make. If it doesn't get initialized, and it's just got some sort of random value in it, then that could easily be X when you get started. So we then have C gets the value of getChar. Obviously, what really should have happened is that this piece of code, those of you who are C programmers, should have gone right up in here and then been checked against X, which makes it a little harder to read perhaps, but ensures that we do initialize the variable. Now, it's also possible that you could get stuck in an infinite loop here because if C gets set to -1, which it will on EOF before, if an EOF occurs, and there's never any X, then this would get stuck and it would loop, because there is no check to see if you got a -1, which, as I said, is what getChar is going to return in the case of an end of file. Which then brings up, so that's this problem, and then that brings up another issue, which is the assignment of an integer value to char value C. That is true. getChar returns an integer. It has to, because a character value, a char value, is by default unsigned. It's an unsigned integer. of some sort or another, depending on whether we're dealing with a single byte or multiple byte character set. So the problem is what you're going to get here is you're going to get a forced casting of this value into this unsigned, which means that even the -1 is potentially going to be lost, because if you assign it to C, then -1 might get interpreted as, well, if it's a single byte, then it's going to be 255. And so in that case, then even if you did have a check for end of file, if you're checking against C, you're checking for an unsigned number to be compared against a -1, which is, impossible, can't happen. So that's explaining about that. And we have another very common mistake, the use of an assignment expression rather than a relational expression. What we wanted here was the double equal signs for relational. We had a single equal sign, which is, of course, assignment, so that's a bug. And that actually produces two warnings here, two problems, and it says that the expression is not Boolean, which it isn't. An assignment statement returns the value of the variable on the or a type, excuse me, the variable on the left-hand side of the assignment expression, which in this case is C, and it specifically returns the value that was assigned to C, and this allows you to have multiple assignment statements kind of glued together to form a single long assignment statement. You can set like 10 variables to be equal to 0 this way. But in this case, it's saying, hey, wait a minute, you can't do that. And then also we have a number of fall-through cases. There is no break here, which is probably on purpose, but there's also no break here, which can result in us falling through into the default, which certainly is not what we would want. So this is an example where we're actually finding real, honest to God, if you will, control flow bugs in the code using a static analysis. Oops, let me go back and get this back in its normal mode. And there's another Java version or Java program for this called CheckStyle, and can check various comments and look at naming conventions and do cyclomatic complexity, which we just looked at that. Make sure that there are headers present on functions. Try to enforce that. Look for what are called magic numbers, which are hard-coded constants. Proper use of white spacing and line breaks and so forth. Class construction, duplicated code. This is always a bugaboo when it comes up, where instead of modularizing a piece of code as a function, somebody's in a rush, and so they just copy a piece of code that's going to be used, copy some logic that's going to be used somewhere else. It's a piece of code. They've duplicated it now. That piece of code has to change. Guess what? It's a change in two places. Usually one place gets fixed and the other doesn't. So this is a good thing to do, is looking for these kinds of duplicated code, and then also looking at readability issues of various sorts. Okay, so that is an overview, which I hope is helpful to you, of application of static analysis to find particular types of defects related to complexity in the code flow, and also actual problems in the logic, as well as stylistic issues. So, up until now, we've been looking at, as I said, the Outbreak, various kinds of behavioral-based tests. In other words, we're running things and looking at how the code behaves, or we're looking at the coverage of the code. So this is kind of a shift. We've looked now at how to evaluate the quality of the code directly. And as I mentioned, one of the reasons that this is so valuable is that not only can it find defects that might be hard to find in testing, it also finds them cheap, and it can find them very early. So that's always nice. Cheap and early are always good, huh? Okay, so as as always, I will put up the advertisement here. So we concluded the presentation itself, so I'll take questions. Any questions that you might have. Give me just a moment to get the rather clunky question block up here. Oops. Bear with me here. Let's see. A question from Rich Agnello. Rich, good to see you again. Let's see. For the ISTQB Advanced Test Manager exam, is the understanding of this material at the K2 level applied K3 in the exam the best approach? Oh, well, for the Advanced Test Manager, this material is actually of limited applicability, let's say. Some of this stuff might be familiar to you from the foundation level, and to the extent that something was presented at the foundation level, if you're taking the Advanced Test Manager exam, you can expect to run into it, maybe, possibly. We're more likely to run into this stuff at the Advanced Technical Test Analyst exam, which is where you would these kinds of materials and more would be covered in great detail. So, but for the Test Manager, I wouldn't worry about it. I see that we have a response on the cyclomatic complexity from Dave Munns, but Dave Munns has left, sadly, because he actually had the right answer. So that's unfortunate. We'll see if anybody else comes up with the right answer. In fact, just to make this interesting, let's go ahead and put that sample code back up. I want to take a quick look at it. Somebody else. Martin has got the right answer. Yavor has got the right answer. Yeah. See if some other right answers come trickling in here over the next couple minutes. I take it that icon, Martin, is the hands sticking up in the air celebrating. That's an interesting one. I haven't seen that one before. Hajo, oh, I see, yes, Martin, happy QA engineer. Hajo, yeah, okay, I accept your excuse, more of a test manager type. Take another look at this, Hajo. I think you might be missing something. Don't just try to, like I said before, count up the branching and looping statements and see what you get. All right, so questions via email here as the answers are trickling in. Question, if we use static analysis tools, do we need to do reviews? Yes, you should, and the reason is that they will tend to find different kinds of defects. Now, when I say different kinds of defects, I mean it's not as if there's a non-overlapping set of defects that would be located. They certainly some of them would be in common, but there are others that would tend to be located by the static analysis that the reviews could not. For example, finding dead code and dead variables is really difficult for the human mind to do, but for a tool it's trivial. So what I would recommend is yes, use them both. Which brings us to the next question of what's the best practice for using static analysis tools as part of a larger process. So here's what we recommend for our clients. Have the developers write their code and their unit tests, or the other way around if you're doing TDD, and then run the tests, fix the problems that are located by those tests, submit the code to some sort of static analysis, fix those problems, and then finally bring the code, the unit test results, and the static analysis results to a code review, and use some sort of structured technique like a walkthrough or an inspection to check the code. And that's going to result cumulatively in a very high defect removal effectiveness. I mean, even if you assume that each one of those steps, the unit testing, the static analysis, and the review only has a 50% defect removal effectiveness, cumulatively you're going to get a very high percentage. I mean, assume that 100 defects introduced into a set of code that's going to go through a review, and we go through those 3 steps. So we remove 50% in the unit test, that leaves 50. We do another 50% in the static analysis, that leaves 25, and then we leave 50% in the review, which leaves 13. So we've got an 87% defect removal effectiveness on that, and typically your process is actually going to have a higher capability than 50%, if at least in the review and possibly also in the static analysis. Unit testing does tend to tap out at about 50% defect removal effectiveness if you're doing following best practices, like I mentioned, of getting at least statement and decision coverage in your unit tests. So that's the process that we would recommend for our clients. I see Chris has clocked in with the right answer here. Chris Randall, yes, that is correct. John asks, John Steinmetz, good to see you again, John. Can you share some quantitative support for the value of static testing? How to prove to others that static analysis is time and money well spent? Well, let's see. Let's start with the money piece. There is plenty of freeware. There are plenty of freeware tools out there to support static analysis. So if the main objection that needs to be overcome is, well, we got no problem with the programmer spending some time cleaning up the quality of their code, but we're not spending any more money on tools, then look for freeware tools, of which there are many, and that can get you a start. Now, maybe the freeware tools aren't as good as what you want or need or what have you, but at least that could get you started doing some static analysis so that you could gather some metrics that are useful in making the justification to invest in the more capable commercial tools. And I'm not saying that all the commercial tools are more capable. I'm just saying that you might have to settle on an open source tool that is not as good as a freeware or as a commercial tool that you might want, but getting started with the open source and then converting over to the commercial tool is less of a problem than it would be that if you were producing, say, a suite of automated functional regression tests, where changing a tool after you got started doing that would be a real hassle. Get started. If that's the objection, it is money. Again, get started with a freeware one, and go off and use that, and then what you want to do is start to look at the relative amount of effort of defects removed in testing and in production versus defects that were removed in static analysis. I mean, if you just ask programmers, hey, when you're using these static analysis tools, when you come to the review, you don't have to say what types of problems you found with static analysis. Just keep track of how many problems you found, and then have them report that, and also how much effort they spent. Just thumbnail kind of thing, because it's not going to be much. And just quick estimates. I spent an hour resolving 15 problems or let's say 10 problems, right? So 6 minutes per problem. Well, that's just minuscule compared to what it's going to cost you to deal with a defect in testing, not to mention production in terms of the time spent. So usually, these kind of questions of the quantitative support for value of some sort of testing activity, I end up falling back on that, relative effort, which some of you listening will recognize as cost of quality analysis, a form of cost of quality analysis. I believe we've done a webinar on this. You can go check some of the recorded webinars and see if not, I'll make sure to put one up. If any of you remember for sure that I haven't done one, send me an email and say, hey, Rex, do a cost of quality webinar. Let's go through this again, because it's a very useful technique for answering exactly the kind of question that you've got, John. And this is an important question because these objections will come up. Now, fortunately, the advent of agile techniques has actually brought a lot of attention back onto not just good unit testing practices, but also static analysis. And we can hope that that attention continues and that people remain focused on code quality and so forth. I remember just, I don't know, about 3 or 4 months ago, I was doing an assessment. I had a client, one of their programmers said to me that, he was talking about all the static analysis and unit testing he was doing. He said, "Oh yeah, we spend a lot of time around here just, talking about how to write better code." And I thought, man, this is really great to hear because, I mean, it's a change in focus, and I'm not saying that programmers in general are not quality focused and they're not people who care about the quality of the work. Of course they are. Any professional cares about the quality of their work, but I think there's been a sort of a long dry spell in terms of tool support for that and just sort of methodological support for that Agile is helping to fill. So that's good stuff, I think. Let's see. Martin says, "Many thanks for the great info, Rex. Looking forward to the next one." Thank you, Martin, for attending. Wanda, I think you might be missing something here. Remember, the rule is count up the branching and looping constructs and add 1 to it. So I'll give you guys the answer in just a minute. Let's see, one more email question. I've heard static analysis can result in large numbers of false positives when first used. How do we handle this? Yes, I mentioned that earlier. We can get a large number of false positives, and basically, here's a strategy that we recommend for our clients that has worked, I think, reasonably well. You basically say that you've got existing code. You're going to first you configure your coding standard enforcement in the static analysis tool to enforce only rules that you think are actually going to matter. So usually you can go through these tools and look at the rules that they're enforcing and say, okay, yeah, that works, or no, we don't really need that one. Then what you want to do is apply that to the to only new and changed code. So you require the static analysis against only new and changed code. So if somebody's writing a brand new module, then it has to pass through the static analysis, and any deviations from standard set for the static analysis have to be approved by the technical lead in the group. At that point, if there are any exceptions, those are set as permanent exceptions, and it's never flagged as a problem before. A lot of these static analysis tools will allow you to do that. And then if somebody changes a piece of code to fix bugs, they're also supposed to put it through the static analysis, though the standard for granting exceptions should be a lot looser in the case of changed code, because again, you don't want to introduce problems where no problems currently exist, or at least no failures are currently occurring. And we found that rule is very, very helpful. So that is what I would suggest. Karen comes back with the right answer on the cyclomatic complexity, as now Wanda does. So let me go ahead and show you why the right answer is indeed 4. Okay, get the magic marker out. Okay, there's a branching or looping construct. That's an if. There's a branching or looping construct. That's a while. And there's another branching or looping construct, which is the if. So we got 1, 2, 3 branching and looping constructs plus 1 is 4. So that is the correct answer. So very good. Whoops, pardon me. Back to the advertisement here. Let's see. Other questions. No, it looks like we've gotten through the questions. So close this session. Let me tell you a little bit more about the resources available through RBCS. We run these free webinar sessions once a month. Please check our webinar site, www.rbcs-us.com, to sign up. If you'd like a special webinar presentation for your company only of this webinar or on any other topic related to software testing, please contact us at info@rbcs-us.com or via our website. If you don't already receive our regular free newsletter, sign up at www.rbcs-us.com. By signing up, you'll get valuable discounts on consulting and training services, along with a regular newsletter that includes a featured article on software testing and quality and news about what RBCS and its partners are doing lately. You can follow us on Twitter at twitter.com/RBCS and on Facebook at facebook.com/pages/RBCS-INC. Remember to check your email over the next couple days because you might be the lucky winner of a free e-learning course from RBCS. You are registered for a random drawing for such a course simply by attending this free event. Check out my blog, www.rbcs-us.com/blog. Feel free to post comments on any of the existing blog posts, or if you have a topic that you'd like to discuss with me on the blog, send an email to info@rbcs-us.com and use subject line that includes the phrase blog topic or something like that, and when I get a chance I will post it out there and we'll start the discussion. Finally, check out the digital library to get recordings of these webinars, podcasts, and videos. You can subscribe to our podcast via iTunes by entering RBCS Podcast into the search string, or see the videos and recorded podcasts by subscribing to the RBCS channel on YouTube. We offer these free resources as a service to the software testing community because, as I said, at RBCS, we're a not-just-for-profit company. This concludes the webinar. I would like to thank everyone for joining us today. Have a great afternoon or evening or whatever is coming up for you in the future. Goodbye.